Now, before we move on, I want to talk about some quantum mechanics and how that relates to statistical properties. So that is section 12.2.2 of the book, Quantum Mechanics and Statistical Properties. So what is the main problem of statistical mechanics? The main problem of statistical mechanics is to count the number of microstates that correspond to a particular distribution, where a microstate actually relates to the quantum state of all the particles that are in the particular state. Now, when these particles are identical, we cannot define particularly which particle is in the particular state. So microstates are completely specified by just stating how many particles are, in fact, in that state. So we defined the fermions and bosons based on the number of ways of arranging the particles, or in fact, on their multiplicity. Quantum mechanics actually provides more ways to distinguish between fermions and bosons than just this one explanation. In this case, we will redefine bosons and fermions based on quantum mechanical considerations, which include, number one, symmetry rules. Suppose we define our quantum state as a two-particle wave function. Suppose we define in a system of two identical, indistinguishable particles, a quantum state as a two-particle wave function given by psi 1 and 2, where 1 gives the coordinates, space and spin of particle 1, and 2 gives all coordinates, space and spin of particle 2. And we say that in order for psi 1, 2 to be a function, to be a valid function, two conditions of quantum mechanics must be satisfied. Those are, 1, psi must be a valid solution of the Schrodinger's equation. And 2, psi must also satisfy the symmetry requirements for the interchange of the two spatial labels. So, for example, they can either be symmetric or they can be antisymmetric. Now, what does that mean? So that means that if an operator operates on it in such a way that the particles are exchanged, 1 and 2 become opposite, then if there is a plus sign that happens, then those particles are called symmetric. And if a minus sign pops up, those are called antisymmetric. So basically, symmetrical particles, if an operator operates on 1 and 2, and it exchanges 1 and 2, however, the value of this exchange is the same as the one it was before, and there is a plus sign that pops up, then this is called symmetric. And the particles that follow this are called bosons. On the other hand, if the exchange particle, if the exchange operator P interchanged it to 2 and 1, however, this value was equal to negative 1 and 2, then this gives you the definition of a fermion. So we say that particles that are antisymmetric with respect to the exchange operator are called fermions. Number 2, occupation rules. So another way to define fermions and bosons is to think about these particles in terms of the number of particles per quantum state. So, or in other words, think of Pauli's exclusion principle. Things that follow Pauli's exclusion principle and things that don't. Pauli's exclusion principle states that some types of particles cannot share the same quantum state, whereas others can. So particles that can share the same quantum states will share the same quantum numbers, whereas particles that cannot will have different quantum numbers. So particles that are subject to Pauli's exclusion principle are called fermions, whereas particles that are not subjected to Pauli's exclusion principle are called bosons. Now, let's write that down. Pauli's exclusion principle states that some types of particles do not share the same quantum state. Those particles are called fermions. Whereas other particles called bosons are not subject to Pauli's exclusion principle. Basically, you can put many particles in the same quantum states if they are bosons. So in other words, we can say that in the orbital model, very briefly, we can say in the orbital model of non-interacting particles, occupancy rules are as follows. Number one, any orbital can be occupied by 0 or maximum 1 fermion of the same kind, determined by Pauli's exclusion principle. And number two, any orbital may be occupied by any number of bosons of the same kind. So number three, distribution function. So what is a distribution function? Distribution function is very simple. It is a mean occupation number of the state with energy E. So what is a distribution function? A distribution function is defined as the mean occupation number of the state with energy E. So for the fermions, the distribution function was first introduced in 1926 by Fermi and Dirac. It is called the Fermi-Dirac function. And it gives the probability of occupancy of energy levels by fermions. And it's mathematically given as 1 over e to the power e minus mu over kt minus 1, where e is the energy and mu is the chemical potential that we have been talking about, and t is the temperature, and k is the Boltzmann constant. On the other hand, for a boson, the occupation number was first, or the distribution number was first introduced in 1924. It is called the Bose-Einstein distribution function. And it gives the probability of occupancy of energy levels by bosons. And mathematically, it is again given as n, f as a function of e, and this is just going to be e minus mu over kt minus 1.